There is a particular quality to the Jurassic landscape at its fullest, a scale that seems designed to make every living thing feel small. The forests are massive, the fern savannas stretch unbroken to the horizon, and moving through them, unhurried and seemingly indifferent to anything that moves at their feet, are the giants. Nothing in Earth's history, before or since, has produced land animals quite like the sauropods of the Jurassic period. They were not simply large. They were large in a way that requires new vocabulary to describe, the kind of large that changes an ecosystem not just by consuming it, but by physically restructuring it. They knocked over trees. They created clearings that became habitat for hundreds of species. They compacted soil with each step, reshaping the hydrology of entire valleys. They moved rivers of vegetation through their bodies and returned the nutrients to the earth in quantities that fertilized the very plants they depended on. They were, in the most literal sense, ecological engineers on a geological scale. To understand the Jurassic, you have to understand the sauropods. And to understand the sauropods, you have to begin with a question that seems almost too basic: how did they get so big? The answer lives in the intersection of several unlikely traits. Sauropods had hollow vertebrae, an extraordinary adaptation that allowed them to build enormous spines without the prohibitive weight that solid bone would have required. The internal architecture of their vertebrae was honeycombed with air spaces in a way that is almost fractal in its efficiency, removing mass from precisely the places where mass was least structurally necessary. They had a respiratory system functionally similar to that of modern birds, with air sacs extending through the body, ensuring a continuous, one-way flow of oxygen that made their metabolism dramatically more efficient than that of any mammal. They grew fast, producing bone at rates more similar to modern birds than to reptiles, reaching near adult size in perhaps 15 to 20 years, then continuing to grow more slowly for decades afterward. They did not chew their food, swallowing vegetation whole and relying on fermentation and possibly gastroliths, swallowed stones, to process it internally. Brachiosaurus altithorax was not the largest sauropod that ever lived, but it was among the most visually striking. Where most sauropods carried their necks nearly horizontal to the ground, using their reach to sweep vast areas of low vegetation, Brachiosaurus held its neck angled upward, more like a giraffe than a whale. It browsed in the forest canopy, reaching into the treetops where no ground-feeding herbivore could follow. At the crown of its 15-meter neck, a small, blunt-toothed head worked methodically through the high branches of conifers and tree ferns, stripping foliage with a raking bite and swallowing without pausing to chew. It is estimated to have consumed somewhere between 200 and 400 kilograms of plant material per day. On the same landscape, Diplodocus longus offered a different approach. Lower slung, longer bodied, with a neck that swept horizontally in wide arcs, it was a ground-level specialist, a creature designed to process vast quantities of low-lying ferns and horsetails. Its neck alone could extend 14 meters. Its tail, whip-like and tapering to a fine point, may in some species have been capable of producing a sonic crack as a defensive or communicative signal. Diplodocus possessed a remarkable skull, slender, with peg-like teeth confined to the front of the jaw, designed not for chewing but for raking and stripping. The animal fed with extraordinary efficiency, sweeping its neck across wide arcs with mechanical repetition. And then there is Nigersaurus takiti, perhaps the most specialized sauropod feeder ever discovered. Found in what is now Niger, this relatively small sauropod possessed a skull unlike any other dinosaurs, enormously wide and spatula-shaped, with rows of hundreds of small, tightly packed replacement teeth arranged in a straight line across the front of its jaws. It was a living lawnmower, adapted to crop the low-growing ground cover of Cretaceous floodplains with a precision that Diplodocus could not have matched. Together these animals, browsing the high canopy, sweeping the mid-level, cropping the ground, formed a layered feeding structure that maximized the extraction of energy from Jurassic plant communities. They did not simply eat the landscape. They partitioned it with an ecological sophistication that took millions of years to assemble. Watching a herd of Diplodocus is to watch something almost geologic in its slow authority. The earth vibrates faintly with each step. The vegetation bends and breaks in their wake, creating pathways through the undergrowth that smaller animals follow for days afterward. Small feathered dinosaurs move in loose flocks through the disturbed air above the herd, catching the insects that scatter before the great feet. A young Diplodocus, still perhaps 8 meters long, its bones not yet fully dense, moves slightly too far from the group in the early afternoon, drawn by a stand of fresh horsetails growing near a small stream. The distance from the herd is not great by human standards. Perhaps 100 meters. But 100 meters, in the currency of predator detection, is significant. Allosaurus does not approach in a straight line. It moves in a wide arc, using a low ridge of ground to break its silhouette, keeping downwind. It does not rush. Rushing a creature this large would be wasteful. Instead, the predator moves in stages, pausing each time the young sauropod lifts its head. When the head goes down to feed again, the Allosaurus advances. The attack, when it comes, is nothing like a decisive killing blow. It is instead a strike at the hindquarters, claws raking the flank, teeth sinking briefly into muscle before releasing. And then the predator backs away. It is waiting for the wound. For the blood loss. For the moment when the vast animal begins to slow. Not all hunts ended this way. Many sauropods drove off predators with a sweep of the tail or simply by moving into the herd, where the sheer density of enormous bodies made attack impractical. Sauropod nesting sites, found across multiple continents, show evidence of communal laying, dozens of females depositing eggs in the same location in the same season, a strategy that overwhelmed predators with more targets than they could possibly consume. Stegosaurus stenops, perhaps the most visually distinctive of all Jurassic dinosaurs, moved through the Morrison Formation landscape on 4 heavy legs, the double row of large, diamond-shaped plates along its back almost certainly involved in thermoregulation and display, richly vascularized, capable of flushing with blood to change color, and large enough to be visible across the distances at which Stegosaurus communicated. At its tail's end, for bony spikes, the thagomizer, as paleontologists have informally named it, were an entirely different matter. Scarred Allosaurus tail vertebrae found in the Morrison Formation bear wounds consistent with a Stegosaurus tail spike delivered at force, evidence of a defensive weapon used with real and sometimes fatal effect. The Jurassic ecosystem, at its peak, was a world of extraordinary abundance and extraordinary scale. The great herbivores moved through it like slow weather, changing everything they touched. They dominated for millions of years. And even as the world began to shift around them, even as the Jurassic gave way to the Cretaceous and the continents drifted apart, the descendants of these giants continued to walk the earth. The age of giants was not, it turned out, something that could be easily brought to an end.